Hello fellas and welcome to another video of Epoxy channel. In this video we will explore polysulfide epoxy systems, their unique chemistry, key properties and versatile applications across various industries. Let's begin with a fascinating family of materials that often files under the radar, polysulfides. These are not your everyday polymers. What makes them stand out is their backbone, made up of chains of sulfur atoms, and that unique structures give rise to some truly exceptional properties. Polysulfide-based sealants and adhesives are elastic, tough, and remarkably resistant to aggressive chemicals. This makes them a top choice in places where things move, shift, or get exposed to petrochemicals like fuel systems, chemical plants, or even construction joints that must withstand constant stresses. They help prevent leaks, protect the environment, and stay strong where other materials might fail. We typically see them in two main forms. One component polysulfide sealants, which are widely used in construction and they are easy to apply, flexible, and reliable. Then there is a two-component system, often blended with epoxy resins. These hybrids offer greater toughness and impact resistance, though with a slight trade-off in tensile strength compared to pure epoxy. Still, what you gain is flexibility and endurance, especially where it counts. What really sets polysulfide apart is their resistance not just to chemicals but also to ozone, salt water, UV exposure, and even fuel. They are built for tough environments. Now, historically, polysulfide started out as a solid, rubber-like materials packed with up to 80% sulfur. But today, the go-to version is a liquid polysulfide polymer, also known as a mercaptan-terminated polymer. These liquids typically contain around 37% bound sulfur, can cure into strong, flexible rubber even at low temperatures. That transformation from liquid to solid right inside is one of their key strengths. So with that foundation in place, let's zoom in and explore how these materials perform in sealants and adhesives and why they are still considered irreplaceable in so many demanding applications.
Although sealants and adhesives often look alike, thick paste or viscous liquids that cure into solid forms, their roles in industry are fundamentally different. Both are indispensable in fields like constructions, automotive, aerospace, and manufacturing, but they are share very distinct properties. Let's break it down. Sealants are specialists in flexibilities, weather resistance, and gap filling. You will find them lining windows, sealing expansion joints, and protecting marine structures. Anywhere that movement and exposure to the elements are part of the job. Adhesives, by contrast, are designed for strength. When the goal is to bond materials together with mechanical integrity, think of joining metals, laminating composites, or building load-bearing parts. These are the places that adhesives are the go-to solution. Now there are hybrid technologies emerging today, like flexible epoxies and sealant-modified polymers that blur the lines and serves dual roles. But even in these cases, one function usually dominates. So how exactly do sealants and adhesives compare? Let's go step by step. First, their primary function. Sealants are the mean for seal, the, to prevent the intrusion of air, water, chemicals, or dusted joints and interfaces. Adhesives, on the other hand, are formulated to create strong bonds between materials, holding things together under stress. In terms of strength, sealants typically provide low to moderate mechanical strength. They are not designed to carry loads. Adhesives, especially structural types, are all about the strength. They can bear significant forces and are often relied upon in critical assemblies. When we talk about flexibility, sealants take the lead. After curing, they remain elastic, which allows them to accommodate expansion, contraction, or vibration. Adhesives are generally more rigid once cured, although some offer controlled flexibility. For gap filling, sealants again have the advantage. They are engineering to span large or irregular gaps and still perform. Adhesives, by contrast, are most effective in thin bond lines. Their large gaps may compromise their integrity. A critical property for many applications is movement tolerance. Sealants are especially designed to move with the joint, handling expansion, contraction, or dynamic stresses. Most adhesives, particularly rigid ones like epoxies or cyanoacrylates, do not tolerate much movement after cure. Their curing mechanisms also differ. Sealants offer cure by reacting with moisture, air, or via simple one-part chemistries. Adhesives may need a more controlled approach, like two-component mixing, heat, or UV activation for fully curing. Chemically, they draw from different toolkits. Sealants are often based on silicone, polyurethanes, polysulfates, or acrylics, all selected for flexibility and resistance to the elements. Adhesives, meanwhile, have a broader chemical range, including epoxies for structural strength, cyanoacrylates for the bonds, and polyurethanes or acrylics for versatility. Their end users reflect these differences. Sealants are used for waterproofing, glazing, weatherproofing, and filling expansion joints. Adhesives go into structural bonding, electronic assemblies, composites lamination, and more. And finally, let's consider their physical behavior after cure. Sealants remain soft, rubbery, and elastics, ready to move with their environment. Adhesives, in most cases, cure into tough, rigid solids that hold their bond under stresses. Understanding this distinction is essential, especially as we move into the more complex and demanding applications where selecting the right materials or a hybrid can make all the difference. Polysulfide are a class of chemical compounds derived from chains of sulfur atoms. When used in sealants, polysulfide-based polymers offer unique advantages, notably outstanding flexibility even at low temperatures and remarkable resistance to a wide range of chemicals. Polysulfide elastomers were first discovered in 1926 by an American chemist trying to synthesize ethylene glycol for antifreeze. The resulting material was commercialized under the name thiocol, which later becomes a generic term. These elastomers exhibit excellent resistance to solvent and lubricants. Typically, they're used in the form of low molecular weight liquids that cure into elastomeric seals. High sulfur content, around 80% by weight, imparts density and excellent hydrocarbon oil resistance. However, the weak sulfur-sulfur bond also contributes to creep and flow under pressure. Plus, polysulfide adhesives are available in both one-component and two-component systems. Two-part polysulfides cure through a chemical reaction upon mixings, allowing relatively fast curing regardless of the ambient conditions. They offer excellent chemical resistance, low shrinkage, and flexibility at low temperatures. However, their strengths drop about 121 centigrades and they emit a characteristically unpleasant odor. One-part polysulfide adhesives are typically used in constructions but cure very slowly. Two-part systems are tougher and more resilient, offering good impact resistance. Thanks to their fuel resistance, they are widely used in aerospace, especially for sealing fuel tanks. Historically, polysulfide polymer referred specifically to high-sulfur polymers developed by the Thiokol Corporation. Between 1928 and 1960s, these were the only available high-sulfur polymers. Solid versions cloth contained up to 82% bound sulfur, while liquid types contained around 37%, giving them their distinctive properties. Polysulfide sealants quickly gained popularity due to their flexibility, adhesion, and chemical resistance. They were among the first liquid polymers to cure at room temperature, a breakthrough that led to their use in military applications. Today, their use is mostly limited to sealants and insulating glasses. Urethanes and silicones with superior properties have largely displaced them in many markets. Despite being somewhat niche today, polysulfide adhesives and sealants remain vital in specific industries, electronics, automotive, appliances, and more. Their applications range from aircraft fuel tanks to electrical pulsing, industrial tank liners, offshore corrosion protection, and vibration demanding for optical devices. In construction, they are used for sealing joints, channels, and areas requiring waterproofing, like dams, culverts, reservoirs, and high traffic public areas. Their flexibility makes them perfect for joints that undergo thermal or mechanical movement. One of the hallmark features of polysulfide sealants is their extremely long service life and robust adhesion. Their water vapor tightness makes them the material for choice in insulating glass to prevent condensation. Moreover, their chemical resistance makes them invaluable in hazardous environments such as filling stations, chemical plants, and spill contaminant areas where environmental contamination must be avoided. Polysulfide sealants maintain durable flexibility throughout their service life. This allows them to accommodate structural movements in critical areas such as airport runways, parking decks, and bridge joints. Their ability to deform and recover repeatedly without cracking is a key advantage. Another core feature is liquid and gas tightness. Polysulfide seals provide reliable, impermeable barriers that resist aggressive substances like hydrocarbons, acids, and solvents. Their chemical resistance makes them a top choice in fuel-rich environments. Lastly, polysulfide sealants exhibit strong weathering performance. They are less sensitive to moisture and can continue to cure even if exposed to rain or humidity, a feature that makes them ideal for outdoor and all-weather applications.
Let's now explore the main types of polysulfide adhesives and sealants that are used across industries. These types differ in structure, application method, and performance. The most common type is the two-component polysulfide systems, also known as the 2K system. This system consists of two separate parts, a base component, which is a liquid polysulfide polymer containing terminal thiol groups, and a curing agent, typically an oxidizing compound such as manganese dioxide or a peroxide. When the two parts are mixed, a chemical reaction occurs that links the thiol groups together, forming strong disulfide bonds. This curing process results in an elastomer with exceptional chemical and fuel resistance. These sealants are widely used in aircraft fuel tanks, bridge and runway joints, insulating glass units, and industrial environments that require robust chemical resistance. Though these systems offer excellent flexibility and aging resistance, They cure slowly, although the reaction can be accelerated when needed. The one-component polysulfide system, or 1K system, is less common and intended for applications where ease of use is more critical than extreme performance. These systems cure through exposure to moisture or air and are often pre-cross-linked to enhance shelf life. They are typically used for light-duty sealing in construction or industrial applications. However, one-part systems lack the high mechanical strength and chemical resistance seen in two-component formulations. To enhance the properties of traditional polysulfides, modified or hybrid polysulfide systems have been developed. These materials are created by bleeding or copolymerization polysulfide chains with other polymers such as epoxy resins for improved strength, polyurethanes for better elasticity and adhesion, or acrylics for faster curing and UV resistance. Such hybrid systems are chosen when a balance of properties is required, for example, in joint sealants or adhesives that must resist chemicals while also offering mechanical performance or aesthetic benefits. Low modulus polysulfide sealants are specifically designed for application involving significant movement, such as bridge decks, airport runways, and structural glazing systems. These sealants remain highly flexible over time and can accommodate joint expansion and contraction due to temperature changes or structural movement. They also comply with international performance standards like ASTM-C 920 and provide long-term resistance to UV light, ozone, and environmental weathering. Finally, fuel-resistant aerospace polysulfides are a specialized category developed for sealing integral fuel tanks and critical aircraft components. These formulations are qualified under military specifications such as MIL/PRF 81 733 and are engineered for maximum chemical resistance and reliable performance in extreme conditions. Typically provided in pre-measured kits, they allow for precise mixing and controlled curing, which is essential in aerospace manufacturing and maintenance environments. Let's now explore the chemistry behind liquid polysulfide sealants, specifically how these polymers are synthesized. The production of liquid polysulfide polymers begins with an aqueous polymerization reaction. In this process, short-chain organic dihalides such as bis-2-chloroethylformol are reacted with sodium polysulfide in water. This forms a flexible polymer backbone rich in sulfur atoms. The reaction is carried out in the presence of specific emulsifying and nucleating agents to control the reaction conditions. The sulfur content in the resulting polymer includes both disulfides and trisulfide linkages, which contribute to the unique chemical resistance and elasticity of the final material. In the next step, this high molecular weight polymer is broken down into shorter chain segments, each terminated by reactive mercaptan groups, or thiols. This step is critical because it prepares the polymer for later curing reactions, where these terminal thiol groups will react to form disulfide bridges. The molecular weight of the resulting liquid polymer is carefully controlled by adjusting the amount of splitting salts used in this step. The typical target molecular weight is around 4,000 grams per mole, and the resulting structure is often represented by the average formula shown on screen. An important part of the process involves controlling the polymer's final structure through the use of a branching or cross-linking agent, usually 1,2,3,3-chloropropane or TCP. This compound introduces points along the polymer backbone that can later form crosslinks during curing. Two common commercial grades of polysulfide polymers are produced using this approach. For example, LP/2 is synthesized with about 2 moles percent TCP, which results in a higher degree of branching. In contrast, LP32 uses only about 0.5% TCP, leading to a more linear structure. Reducing the amount of cross-linking agent produces a more flexible polymer with a lower modulus and higher elongation. This is especially useful in applications that require the sealant to accommodate large joint movements, such as in bridge expansion joints or runaways.
Now this is time to end this session, and I hope you enjoy. Stay tuned for the next slides on this fascinating topic. Thank you.